Hello, this is the OLED Auditorium. I'm Seth Sullivan, co-founder and CTO of QD Vision, and today I'll be talking to you about color and quantum dots. Just for a little bit of background, QD Vision is a company that spun out of MIT about 10 years ago. We have operations in Lexington, Massachusetts, just outside of Boston, as well as overseas in Taiwan. We currently have some 250 patents and patents pending, and are quite proud of being the first in the world to bring quantum dots to both the display industry as well as the lighting industry over our 10-year history. We have large manufacturing facilities here in the US as well as in Taiwan, and are currently developing products and in the market with products with the top display companies in the world in China, Europe, and Japan. Our vision, our purpose, we really see as delivering the most colors across the most applications and devices to the most people. And I think as this talk continues, you'll get a sense of what we mean by all three of those things. For purposes of this discussion, we'll really focus on what we mean by the most colors and what that means to the display industry. As a display community, and I think particularly to this OLED-focused audience, it should be clear that the display industry has invested billions in image quality. As an industry, I think whether we're talking about plasma, LCD, OLED, we've clearly made great progress on display size, where average displays now are well into the 40-inch regime. Resolutions, we're in the middle of a major transition from full HD or 2K to 4K resolution displays. Contrast, something that OLED in particular excels on, as well as brightness, and I think these are all very important display metrics. But if you ask a consumer, an advertiser, a doctor, what they really think of when you think of image quality, I think resolution is on people's minds, but they all across the board will talk to you about the importance of color, how color is important in the work that they do, in the experience that they have when in front of a display device of any type. And so it becomes important to talk about what do we mean when we say better color, and why is it that color is rising in importance to consumers and to the industry. I think on the left, to an OLED audience, this might be obvious, but the difference between what we mean by a desaturated and a saturated color. Obviously, the saturated colors on the right of that chart are more vivid, more brilliant, where on the left everything seems to have sort of a whited out or washed out look and feel to it. And what's interesting is something called the HK effect, that as you get better color, more saturated color, most people will tell you in side-by-side comparisons that they perceive this as higher brightness. And so color is now becoming equivalent with brightness in the battleground that's out there today, particularly on the TV market. In addition, if you look to the chart on the upper right, as an industry and consumers, we've been focused looking backwards on resolution as really important. And so you can see here when we use the 3M display quality score of viewer preference on the y-axis, and just value of the display to consumers on the x-axis, you see that the curve was very steep in terms of preference when we went from, say, 480p to HD, and even from HD to full HD on the red line. But that curve is quickly flattening out for viewers a standard distance away. And so this shift from full HD to UHD, there is benefit. People do appreciate the difference, but we're in a much shallower portion of the curve. And in contrast, the color gamut line, the blue line there, is still in a much steeper regime. And so right now, the majority of TV devices are at or about Rec. 709, having improved a little bit from the 50% NTSC that they were a little while ago. I think the current generation of TVs are really making this push from Rec. 709 to DCI-P3 and NTSC color spaces that we'll talk a bit about later, and even more so this Rec. 2020 space. And so you see a lot of people tying UHD resolution, 4K resolution, to Rec. 2020 color gamut, because in order to get a significant noticeable increase in quality and therefore viewer preference, people are finding that they really need to tie these two display metrics together to have benefit in the market. And so we like to ask, we at QD Vision, we in the quantum dot community, I think we in the OLED community as well, like to ask ourselves, what do we mean by color quality? Why is it that there's still so much room to run on the color axes of these graphs? And so we have to start with the diagram in the upper left here, the so-called CIE diagram, which was made back in 1931. This is a two-dimensional representation of all of the colors that the human eye can perceive. And so you've got a horseshoe shape where red is on the right-hand side of this, blue is on the bottom, and green is on the top. And any color within that space can be perceived by humans, and we can take any visible color and plot it as a point on these two axes. And then when we take a typical display, a typical tricolor display, like any plasma LCD or OLED that's mass-produced on the market today or ever, we can plot those three axes, the three pure color primaries, as points, and then draw a triangle between those three vertices. And again, any area within that triangle can be created on the display screen by mixing the three primaries of the subpixels. And so these color gamut triangles can show us the area, the percentage of perceived colors that a given primary space will render for the viewer. And then this also becomes how standards get written. And so, starting with the current computer standard, Rec. 709, sRGB is the broadcast standard that goes with that in Europe. You can see on the bottom that we're actually only able to render about 36% of the colors that humans can perceive if we have a display that meets that low standard of Rec. 709. And you can see on the CIE diagram that that's the innermost triangle on this plot. And so because the vertices of the triangle are close to the center of the picture, the area of the triangle is smaller, and hence the number of colors that are within that triangle is smaller. What's interesting is that beyond Rec. 709 today, there are a wide range of color standards that are out there depending on the industry you're in. Most TVs today are spec'd in terms of NTSC, what percentage of the NTSC triangle can you render, and you can see that quite a bit larger triangle in the dashed lines on the CIE diagram to the left. If you're in cinema, coming from Hollywood, the digital cinema DCI-P3 color standard is what's the most relevant. By area, it's quite similar to NTSC, but you can see it's got a slightly different green point and red point, and so the areas, while the areas are quite similar, the colors that are actually rendered are a little bit different. And then similarly, Adobe RGB, where this is very useful for the computer graphics world and photography. And so if you're taking a photograph on your SLR camera that you bought for $1,000, you're recording that image in this wide color gamut standard of Adobe RGB. And if you're then trying to display it on your computer at home, typically you've got a Rec. 709 computer, and so you're not actually rendering all of the colors that you recorded. You can see that set of standards, Adobe RGB, NTSC, DCI-P3, on the bottom table there. Now we're up into the 50s of percent, call it 50% of the human perceivable colors. And that's quite a bit more than 35%, but obviously leaves a lot of room for improvement. And so most recently, the ITU published this new so-called Rec. 2020 standard. Some people will call it BT 2020. Back in 2012, they published this, and the idea was to create a much wider color gamut standard. It was somewhat aspirational at the time, but if you had hardware that could support this wider color gamut, now we'd be at about 76% of the human perceivable colors that could be rendered. And so all of a sudden you're able to create a much more realistic picture. This gamut is now going to encompass a very high percentage of the naturally occurring colors in our world, as well as a much larger percentage of the artificial colors, man-made colors that we find in our largely man-made world today. And so this is something that a lot of people are driving towards. There's a lot of infrastructure, just like 4K or even the transition to HD. There's a full range of technologies that need to go into this to deliver this standard, from the recording to the mastering to the broadcasting of content. But once this content gets to your TV, there needs to be a TV and a display technology that can render it as well. And people are working on every aspect of those with varying degrees of success. So next we need to get from all of those great color standards to how do we produce a color gamut on a typical display. And here we're going to start from the LCD approach, which is certainly the dominant TV display technology on the market today, but also for most devices of any size. And so what you've got here in blue is the typical spectrum that a white LED backlit LCD will produce front of screen. So this is a white LED. The peak on the left is the blue LED chip. That's the primary light source. It then pumps a phosphor, one or two phosphors that produce yellow in summation, but certainly with some red and green components. And then that light goes through a color filter to separate out the red and green components. And so this actually ends up being quite similar to, say, the current LG white OLED technology, where you have a blue peak and a yellow peak, and you use color filters to produce the three colors of the spectrum. You end up with this very broad set of light, whereas what you'd like to have are very narrow bands of light. And so, for a long time we would compare OLEDs to these white LED LCDs, or even the old CCFL backlit LCDs, and you could very easily see the benefit of OLED, where OLED for mobile, the full color side by side approach for OLED, you have three distinct peaks in red, green, and blue, and hence you were able to get a much broader gamut because you're putting as much light as possible into these narrow red, green, and blue bands by having a peaked approach. But of course the ideal solution is to put all of the light into those bands. And so what quantum dots give you, because of their very narrow band features, in this graph we say 30 to 35 nanometer, full width at half maximum, typical. But you can find commercial products from QD Vision on the market today that go even lower, below 30 nanometers. We're delivering as many of the photons as possible, most of the photons in fact, into very narrow band features. That means more of the light gets through the color filter. We're doing this without any microcavity effects. This is the native light that comes out of the particle without any filtering, and then so really the only role of the color filters in these LCDs is just sorting the red from the green. It's not creating the spectrum in any way. And so then I wanted to come back to this Rec 2020 standard. And so, let's look forward at color in the TV industry and in the display industry generally, and go with this aspirational Rec 2020 standard. If you look at the way the standard was set, they were assuming a theoretical maximum. So, what would be the ideal color gamut that you would choose to put in a display? Clearly, you'd get there most effectively with extremely narrow emitters, and so they assumed, for discreteness sake, a 1 nanometer emitter. So this looks a lot like a 1 nanometer laser line. And then they chose the red, green, blue primary wavelengths, optimizing the trade-off between wide gamut, but then also power efficiency. And so they don't want you to choose a red at 680 nanometers because you'd have very little perceived brightness from the human eye at that wavelength. And so you pick something a little bit more reasonable. Nonetheless, you get this very broad, 75% of the human perceivable colors using these 3 primaries while getting the benefit of color efficiency. So again, this is theoretical. This is unrealizable, but the aspirational standard. So the obvious way to try to solve this problem, if you're essentially modeling it on 1 nanometer laser lines, is why not use lasers to do this? Certainly multimode and single mode lasers, solid state or any other gaseous state lasers exist and have existed for a long time. And you can certainly make a laser-based display. There are people that have been doing this for a long time. Mitsubishi probably is most notable. And you can get some amazingly wide color gamuts. The problem with using lasers has been both in cost and efficiency. And so, from going to the trouble of going from an LED, OLED, quantum dot sort of spontaneous emission system to something that's stimulated emission tend to be much lower efficiency conversion from electricity to light, and so you end up having either very dim displays or very power hungry displays that fail to meet other energy standards such as Energy Star here in the US. And so, the next one you try are using LEDs themselves to do this. Instead of using those broadband phosphors, in this case, we can imagine using separate red, green, and blue LEDs. Again, all of these exist in the market today. There was a big push back in 2005 and 2006 to implement LCD backlights in this way. But you end up with a good color gamut. So here we're showing that you can easily achieve in the high 80s of the Rec 2020 color gamut because you've got semiconductor bandgap emitters in the red, green, and blue. But the particular problem here ends up being in the green. The so-called green gap is in between the 2 dominant semiconductors. You've got Allen gap in the red and indium gallium nitride in the blue. And there's really no natural fit of an easy-to-make semiconductor in the green, and so the efficiencies start to roll off, whether you're making red and trying to pull it to the green or you're making blue and trying to pull it to the green. The efficiency is rolling off in each direction, and that color that you want to make to hit any of these color gamuts, it turns out to be amongst the most difficult. And so the efficiency is very low. Therefore, you need a lot of them to get to the brightness you need, and of course most of the brightness you need is in the green. And so as a result, these are extremely expensive and extremely power hungry as well, in addition to having a lot of complexity due to the different aging of these different material sets in LED land. and so then, the other one that we love to talk about, and most of the people in this audience love to talk about as well, is OLED. Again, being focused on TV for the majority of this discussion, we'll talk about white OLED. And so this is an example of a spectrum that we record from a white OLED on the market. And then, of course, you take this and you put it through the color filters to separate out the red and green bands from that broadband yellow emitter that's in there. And when we look at this, you see that the color gamut in this case is limited to about 66% of the Rec 2020 gamut. No doubt you could do better if you use RGB separate emitters. So far that's been elusive in terms of stability for a white OLED. Clearly you're paying an efficiency penalty here by using color filters, and at least to date, the red, green, blue discrete pixel approach has been elusive at TV sizes. Certainly that's something that you'd have access to in a mobile phone, and the other sort of big variable here is whether or not we're going to use microcavity effects to narrow up these OLED spectrum. Again, so far in TV that's been elusive. Certainly in curved TVs, it seems like something that would fundamentally not work. And so OLED becomes a good color gamut, certainly better than a white LED, but not approaching these other LED and LCD based technologies in terms of color gamut limits. And so then, obviously the one that QD Vision is most interested in and thinks is the best is quantum dots. And here, again, we're going to get that narrowband benefit. We're using semiconductors to make light, and so all of the light is being emitted from that band edge. There isn't that long, low energy tail associated with organic molecules because of all the vibrational modes and floppiness associated with those carbon-carbon bonds. And so we can model and actually make in the lab and entering production very narrow emitters that through standard color filter sets, or even better, some improved color filter sets that are coming to market, we can make something that is up to 97% of the Rec 2020 standard. And so, despite the aspirational nature of this color gamut when it was conceived, 1 nanometer wide laser lines, the combination of doing quite well on the full width half max using semiconductor quantum dots, as well as the flexibility of color filters and how you can filter things out and keep the different bands separate from each other, you can really approach that otherwise aspirational goal. And you can get there quite efficiently as well, because there's not an efficiency trade-off with the narrowness of the quantum dots. We can make these, and routinely do make these emitters, certainly amongst the most efficient emitters in the world, quantum yields that are essentially unity, and even now at high temperatures, where typically quantum yields of organic dyes or other phosphor materials start to get lower. So, it's certainly our opinion that quantum dots today are offering the best mix of both color and efficiency for this BT 2020 standard. And we think this, as this standard gains traction in the market, it's going to be another great driving force to pull quantum dots into the market in LCDs and then eventually as the emitting material in OLEDs. So, just coming back to that quantum dot based LCD, what might be a little bit confusing to people is that there are such different implementations of quantum dots into that device. So they're all in LCDs today. They are all found in the backlight unit of the LCD, and so that's what you see sort of broken apart here. Of course, there's a panel in front of the backlight that actually does the spatial light modulation and the color filtering, but the white light source that is behind all of it can be implemented in these 3 different ways. So it's probably easiest to start in the middle here, where you can take the quantum dots and coat them out in a large area film, and put the quantum dots over the entire surface of the backlight unit. And so now your backlight unit is just comprised of blue LEDs and blue light. As the blue light goes through the red-green quantum dot film, it makes the trichromatic white that we've been talking about in the rest of this talk, and that gets filtered out. This has the advantage of the quantum dots being very far from the light source. It's it's a remote optical component that doesn't have to get very hot and doesn't have to see a lot of flux. And so in many respects, this is the easiest to implement of the quantum dot backlight unit implementations, but it comes at a high cost. And so the quantum dots themselves, there's a lot of material there, and so it can be quite costly. And in addition, for stability reasons, you're going to put some sort of an oxygen barrier around the quantum dots. These aren't the flexible barriers that the OLED world is used to, that are typically 10 to the minus 6 WVTR grams of water vapor per day, but something in the neighborhood of, say, 10 to the minus 2 to 10 to the minus 4. So it's a less costly barrier film than OLEDs typically are requiring for flexible OLEDs, but nonetheless an expensive component. You need 2 sheets of it because you need a front and a back. And so a typical 55-inch TV implementation today, here in 2015, might be $100 to $200, and so this goes into the very high end of TVs today. Nonetheless, this has had a lot of success, and so 3M is offering these films to the market. LMS is offering these films to the market. Samsung is making these materials for their own consumption, and you've seen implementations in the market from Amazon Kindle to an Asus notebook, to a line now of Samsung TVs at the high end of their product line. Next in line is the QD Vision approach, where we'll use an edge optic. And so this is, instead of a film that covers the entire area of the display, just a tube of glass that contains the red-green quantum dot mix in front of the blue LEDs. So we're going to put the quantum dots now between the blue LEDs and the light guide, as opposed to after the light guide in the previous case. So this means that we have a lot less area to cover, and we're using much cheaper barrier materials. Being able to use glass instead of barrier plastic is a huge cost savings, as well as using 1/40th or 50th of the material, of the quantum dot material. So there's some nice cost advantages here. The real challenge is that the materials see about 100 times the optical flux. They operate at about 100 degrees Celsius in a TV because of how close they are to the LED light source. And so there are quite a few material challenges here that needed to be solved before we went to market. Nonetheless, we actually brought this to market before film in a series of Sony TVs, and today you can find this solution in TVs from Sony to Hisense, Conca, Philips, TCL, Thomson, monitor products from AOC and Philips as well. And so this incantation of the quantum dot backlight unit is getting to be quite popular, with a number of brands adopting it. And then the next step after that, assuming there will be one, is to take the remote component away completely and just put the quantum dot down conversion material directly within the LED package. And so now you've got the same thing, blue LEDs, then down conversion with red-green quantum dots, and then that light enters the light guide plate. But you can get away with using even less material. The material does need to see even higher fluxes and even higher temperatures. But you've now gone from, you've basically completely eliminated this remote component. And so you've gone from an implementation in the middle that might be, $100 or $200 price premium, and by the time it gets to the end market, to something that could be, very, very affordable, almost invisible cost uplift to the consumer. And yet get all the benefits of efficiency and color gamut that quantum dots bring. And so, we'll stop with just, a closer look of that QD Vision implementation. Again, the advantages here in terms of cost, the the challenges in terms of higher flux and higher temperature. But nonetheless, like all quantum dot solutions, we're implementing it with an optical component that contains the light-emitting semiconductor material. We're today boosting LCD color performance by about 50%, but as we approach Rec 2020, that will be closer to 100%. And certainly this is the best available wide color gamut efficiency combination on the market today, and this is something that scales quite easily to large implementations in the LCD TV world. Again, perhaps in contrast to OLED, there's no new fab required here. Everything I described to you doesn't enter the LCD fab, the $2 billion of infrastructure that exists. This all happens at the assembly house, at the backlight level, and as a result doesn't require an investment on the part of any of our customers. They simply buy this additional component and can get the benefit of quantum dots in their existing mainstream display device. And so with that, I'll leave you. Hopefully you walk away with a bit more knowledge than you had on quantum dots, on how they're implemented into LCDs, as well as how these different color gamut standards can be approached by various technologies, including quantum dots and OLEDs. Thanks so much for your attention, and I hope you enjoyed it.